and I'm going to introduce my co-chair. He'll be our first talk in this session, David Kring. Its title is Geologic Exploration Training for Lunar Surface Operations, and he's presenting on behalf of co-authors Looper, Ney, and oh, I'm sorry, David, Janico. You can correct that if I was wrong. So go ahead and kick that off.
Okay, Sherry, can you see my slides?
I cannot yet.
Okay, that's what I thought. I had a little bleep here. So.
All right, perfect.
Okay, yeah, that's Barbara Janoiko here at the Johnson Space Center. That's how you say her name. So let me launch quickly into the presentation with this first slide. I need to explain that the project that I want to be summarizing today was requested by Administrator Bridenstine before he left the agency. He asked for some input regarding lunar surface operations, and so our survey-sponsored team, the LPI JSC Center for Lunar Science and Exploration, produced a training report, which I'm going to summarize today. This is the title of the report. It's called Training for Lunar Surface Operations, with the same authors that you saw on the title slide. What we tried to do in this report, or what we were asked to do in this report, is to summarize the lessons learned during 6 years of work with the Constellation program about a decade ago. What some of you may remember is that during Constellation, we were planning to land on the rim of Shackleton Crater near the South Pole and basically begin an exploration of the lunar South Polar region, just as is being described for Artemis. And so a lot of the lessons learned during Constellations are directly applicable to Artemis. And I'm really happy to say, if you've not spied it on the title page there, that the lead flight director for Apollo 15 and 17, Jerry Griffin, wrote a foreword for the report. So I want to walk you through some of the findings. Finding number one is that the Artemis 3 landing site and Artemis base camp within 6 degrees of the lunar South Pole will be in an impact crater terrain, and thus crew should be given basic geologic training and conduct EVA simulations in appropriate analog terrains. Here is some training sites that we've used before in the American Southwest. Included among them are of course, Meteor Crater, which is a classic all the way that goes back to Apollo. We also have in West Texas, the Sierra Madera impact crater, and we have Schooner Crater at the Nevada test site. This is another way of looking at some of those analog sites. So here's a picture of the South Pole, and I have some arrows pointing to a variety of craters within the South Polar region. And I'll just kind of point out some of the analogies that we have. So Meteor Crater, it has the same shape as Shackleton at the South Pole. It's really the best locality in the world for impact crater basics, and was, as you know, an Apollo training site. We might actually want to go afar to, for example, the Ries Crater in Germany. It's similar in size to Shackleton. It's similar in shape to Haworth, Shoemaker, and Faustini, and contains ejected blocks like we see and been mapping it at Shackleton. It also was an Apollo training site. And then Sierra Madera, Texas, closer to the JSC than the Ries Crater, is also a structure that approaches the size of Shackleton and contains an uplifted central peak like other polar craters like Amundsen. Finding number two is that based on Apollo experience, classroom, laboratory, and field-based training for lunar surface conditions may exceed 1,000 hours. So this is a non-trivial amount of time needed for this to address this issue. And it really needs to begin immediately to meet the Artemis schedule. Crew, once selected for a mission, may need to engage in monthly field exercises. Here's an example of what the Apollo 16 crew experienced after they were selected. There was surface-related training. There were 39 sessions for a total of 142 hours. There were simulations using a mission control center. There was some orbital geology studies, some flyover studies, 36 days of field trips, classroom geology lectures, and studies of rocks, for a total of 110 days of training prior to the Apollo 16 flight. It's important to point out that the South Pole resides on the rim of Shackleton Crater, again, an impact crater terrain, and that impact event excavated 4 times 10 to the 11th cubic meters and nearly 1 billion metric tons of rock, okay? Knowing which rock samples to collect from those deposits takes skill that will need to be developed. Moreover, the Shackleton impact event and other impact events in the regions modify the distribution of volatiles, and understanding those impact imposed consequences and evaluating them while engaged in EVA will take skill that needs to be developed through the training that we've just described. And I'm going to quote here Jack Schmidt, something that he said following his mission. A lunar field geologist must always be aware that time is relentless, that consumables are limited, that fatigue can be fatal, and that usually returning to a location is unlikely. These cognitive realities add to the normal intellectual workload of doing field work. For that reason, he added, planning, voice communication, automated location, and sample documentation, and most importantly, field experience all take on an even greater importance than normal. Finding 3, in addition to monthly field exercises, complex mission simulations should be conducted in analog terrains with the integrated expertise of a broad group. That involves the astronaut office, astronaut trainers of all types, geologists involved in surface operations, lunar sample analysts, in situ resource specialists when appropriate, equipment designers, flight controllers, and management. A simulation with all of those people involved will undoubtedly uncover unanticipated challenges, produce a well-working team, and give that team the resiliency to successfully resolve unexpected conditions that may arise during a lunar surface mission. Finding 4, Constellation mission simulations demonstrated an integrated flight and science operations architecture greatly enhances mission productivity. What do we mean by that? In Constellation, we developed a science operations center that was integrated with the standard flight operations center. And so when crew went EVA, there was a handoff from the flight director to a science leader or science lead, and the scientist spoke directly to the crew. That greatly enhanced mission efficiency and productivity. Because of time, I'm monitoring here. I'm going to skip over a couple of slides and go to finding number 5. Apollo experience and the nature of Artemis polar terrain suggests the science team supporting training activities and subsequent lunar surface operations need a management team that has experience in the impact crater terrains that I've described already. Analytical experience with lunar samples. We have the Apollo collection and lunar meteorite collections. Experience in analyzing polar volatiles and experience with the South Polar terrain. Finding 6, Constellation mission simulations demonstrated EVA training for crew is evolving from task-specific training needed for Shuttle International Space Station activities to a skills-based training model needed for lunar surface operation. Skills-based training will become increasingly important as the duration of lunar surface times increase. And that's illustrated with this diagram here, which I've pulled from a paper by Ney and Looper published during the Constellation era. And finding 7,
that'd be great.
Thank you. The development of EVA training needs to be initiated immediately to meet the Artemis schedule. It's important to develop the operational concept and applicable skills in parallel with hardware development. And so here are my final thoughts in the last few seconds. Surface science traverses are a system level activity, not a subsystem activity. Science ops are similar to flight ops in scope and complexity. Field geology is more than knowing how to use a tool. Lunar surface science traverses are not geologic mapping exercises. Sample collection is the most effective way to produce transformative scientific advances. Field geology and surface science traverses are skill-based activities. We need to train to meet mission objectives, but we also need to be prepared to encounter something completely different. Thank you.